this lecture I would be talking about design for testability techniques in digital circuits, which is a very popular technique which people use nowadays in order to add some special testability, you can say sub circuits or some testability hardware inside a given circuit, so as to make the problem of testing much simpler for the test engineers. So, this design for testability is the topic of discussion in this lecture. First, let us see what this DFT or design for testability is and what are the different ways in which you can do it. Design for testability is actually a collection of techniques, design techniques, using which both test generation and test application can be made more manageable and cost effective. Okay. So, when I say both test generation and test application, it means the complexity of the test generation process get reduced and the total time of test application also we try to reduce. Of course, these two are contradictory. Sometimes we will see that test application time will go up, but in some other scheme again it will go down. Now, for digital circuits, there are broadly two approaches which people follow for design for testability. The first one is of course a set of techniques which have been laid down by experienced designers. These are called ad hoc methods. So, designers out of their experience, they know that well, if I have a circuit structure like this becomes difficult for me to test. So, you do not use this. So, there is a big set of do's and don'ts, that means you can do this, you do not do this. There are a big set of ad hoc rules which are totally based on design experience. Okay. These are called the so called ad hoc methods. The second and more structured and regular method is one where there are some well defined techniques which can be integrated in the CAD tool for synthesis also, which results in some circuits which becomes much easier to test. So, there are techniques like scan and partial scan, built in self test, boundary scan. We will briefly look at these, all of these. So, first we look at the ad hoc methods for DFT and what are the different rules that people have proposed. Well, I am only giving you a small set of rules, in fact, the number of rules are pretty large, just to give you an idea. So, the ad hoc DFT methods, these are essentially good design practices which have been laid down by experienced designers who have learned them through design experiences over a period of time. Some simple rules are as follows. You avoid asynchronous feedback. See, avoid asynchronous feedback means it is not good, it is not desirable to have a circuit say like this, where from the output of the OR gate you give a feedback to the input. This is an asynchronous feedback, but the designer will not mind if there were a flip flop in between. If there is a flip flop in between which is controlled by a clock, then this is a synchronous feedback. So, whenever there is a clock, only then the output value will come to the input, it will not come continuously. Okay? Fine. Avoid delay dependent logic. Sometimes we design circuits where the delays of the individual circuit elements are made use of in order to achieve some logic. For example, for generating a very narrow pulse equal to the delay of 1 gate or 3 gates and so on. So, you do not use those things. Monostable multivibrator and logic which can reset itself to a known state, these are not recommended. What designer says that well, if you have to reset some logic or some counter or some register something to a known state, there should be a reset signal which can be given from outside. Say externally you should be able to reset the circuit, not using some logic inside, it is automatically resetting itself. because if there is some problem in the reset logic, it will be very difficult for you to test. Okay. Avoid gated clocks. Clocks should go straight from the primary inputs to the respective clock inputs of the flip flops. You never use a structure where there is a gate, there is a clock in one of the input, there is some logic coming in the other input, and the output you are feeding to a flip flop clock. This is something which is avoidable. So, you do not use gated clock, because if there is any a problem again in the logic which is controlling the clock, then you will be having a lot of problem in testing the circuit. You try to reduce the redundancy as much as possible. So, if you have a circuit realization which is not properly minimized, then it can be shown that there are many faults which can occur and which can prevent the detection of other faults. So, if there is some redundancy in the circuit, your fault coverage can go down significantly. So, you try to reduce redundancy. Do not use high fan in or high fan out, because these are not good in terms of circuit performance and also reliability. So, all the flip flops should be initializable externally with relatively less effort. Okay. If you have a mixed signal kind of a design where both analog and digital circuits are on the same chip, you try to separate them out into disjoint areas of the chip. Do not let the analog circuit and digital circuit, they interact with each other closely and result in unpredictable behavior. And if you find through analysis that there are some difficult to control signals, then you can provide some separate test control for them. For example, inside a circuit, if you find out that this is a signal which externally it is very difficult to test, to control. This is possibly coming from the output of a gate, this was the circuit. So, what you do as a modification is that you introduce a multiplexer. The one input of the multiplexer is coming from the gate, other input is coming from the primary input, and you also have the control of the multiplexer from the primary input. So, by controlling these two lines, you can directly control the value of this logic value if the need arises during testing. Okay. Buses are good in terms of testing, so you try to use buses wherever needed. This I have already mentioned, limit fan in and fan out. And ultimately, you will be doing the testing using some automated test equipments or ATE. So, you will have to look at the requirements of the ATE before you frame the design rules, like whether your tester supports tri-state logic or not, for example. Okay. So, these are some design rules which you can enforce, and the resultant circuit will be easier to test. But as you can see, these are all ad hoc kind of rules. Well, even if you follow these rules, you cannot really quantify that how much easy it will be to test. Okay? This you cannot quantify. Structured design tries to attack the problem from a different viewpoint. See, the structured design for testability, they are primarily focused or aimed to test sequential circuits, and as you know, a sequential circuit can be modeled like this, where the combinational portion and the memory portion, flip flop portion can be separated out. Of course, I have not shown the clock will be there, this will be a clock which will be feeding the flip flops. Primary inputs, primary outputs, and the state variable, this is the present state and this is the next state. So, when the clock comes, the next state becomes the present state. Okay. Now, because of the presence of the flip flop, the problem of testing a sequential circuit becomes difficult, because you try to understand if there are n primary inputs, for example, if there are m number of flip flops, then the combinational circuit can have 2 to the power m plus n combinations. Now, out of these n inputs you can control directly, but the other m inputs you cannot control directly. So, these other m inputs you cannot control directly, this lends the complexity of to this problem, that how easy or how difficult will be to control these flip flops. This will dictate the complexity of this total testing problem. Well, now suppose if we can devise some mechanism using which we can set these flip flops to any known value externally rather easily, and also we can observe the values of these flip flops. So, what we are saying is that we want complete controllability and complete observability of these flip flops. Now, if we can achieve that, then you try to understand one thing. If we can achieve that, then the testing problem reduces to the problem of testing the combination logic alone, because now I can assume that all m plus n inputs are directly controllable, because I can set the flip flop to any known value. So, as if all m plus n inputs are available to me, and similarly all the outputs are also available to me for observation. So, if we do this, the problem reduces to the problem of testing combination logic alone. We can forget flip flops for the time being, okay? And we can use a combinational test generator which is relatively much less complex for generating the test patterns. This is the basic idea behind the structured design for testability techniques. So, one very popular method for this structured design technique is called a scan design or a scan path. The scan design says that you have some kind of simple read write access to all or subset of the flip flops. Well, for the time being we assume all, we shall see later that we can slightly relax this restriction, we can have this access only to a subset of these flip flops also. And using this, what we can achieve? We can have direct control of these storage elements. We can set them to either logic 0 or to logic 1 as the need arises. And the second thing is that we can also observe their values, direct control and direct observation. These are the two aspects of scan design. So, direct observation of the state of storage elements. Okay. So, essentially we are trying to enhance the controllability and observability of the storage elements of the circuit. This is the basics, you can say basic crux behind the scan design technique. Now, scan design technique also follows some design rules, but the design rules are targeted towards achieving the goals as I have just mentioned, to enhance the controllability and observability of the flip flops. Well, and nothing can come free. In order to do this, you have to add something more to the circuit. You have to add a test structure in terms of some additional hardware and extra pins to the design. So, essentially what you need minimum is that you need one extra pin called test control. This extra pin will tell you that whether you are in the normal mode or in the test mode. During testing, the test control pin will be high, otherwise it will be 0, something like that. And you will also have to modify the flip flops. We will see how. You will be replacing each flip flop by so called scan flip flops, and you will be interconnecting them in such a way that during the test mode the flip flops all become a long shift register. Okay. And each of these shift registers, which are called scan shift register, they can be controllable, observable from the primary input output if their inputs and outputs are available. So, what we are doing here is that all the flip flops that exist in our circuit, we add some extra hardware so that if the test control is high in the test mode, they all become chained into a shift register. So, now we have a long shift register, we can shift in any data pattern to that shift register and we can load it with any known value. So, using this we can achieve complete controllability of the flip flops. Similarly, after applying a clock, whatever gets latched in the flip flops, we can again configure them as a shift register and again apply clock to shift out the bits serially, and you can observe them whatever is coming out. So, we can also get complete observability. Okay. So, by configuring the flip flops as a shift register helps us in achieving complete controllability and observability of the individual flip flops. Okay. And once we have done this, we have reduced the problem of testing to combinational logic testing. So, now you can use combinational automated test pattern generator to obtain the tests and some additional tests to test the shift registers. This is all we need. We need to test the shift register, and once we have done this, we can use the combinational test patterns to test the combination logic. Okay. Now, there are some scan design rules, some of this we have already mentioned. This says that you only use clocked D flip flops and at least one primary input pin, that test control, must be available extra. More pins if it is available you can use to your advantage, but minimum one pin must be available. Third, no gated clocks, all clocks must be directly controlled from primary inputs, and clocks must not feed the data inputs of the flip flops. Okay. This is also not allowed. Clocks must only feed the clock inputs of the flip flop, nowhere else. Well, there are ways to enforce these rules. For example, let us take one example, say the third one, all clocks must be controlled from primary input. Suppose in a design, say like this, we had a circuit, a portion of the circuit where this design rule violation was there. Like the clocks were not directly controlled from primary input. That means, here you had a gated clock. This is a flip flop, clock, some other data D2 coming from somewhere, they were ANDed and then the clock was generated. But the rule says the clock should come directly to the gate inputs. Okay. So, this design means that if D2 is 0, okay, the clock will not come and the flip flop will retain its state. So, I can modify this circuit like this in order to eliminate this design rule violation. You see what I have done. Now, this clock is coming straight to the clock input. Okay. Here this is nothing but a simple multiplexer. This is a 2 line to 1 line multiplexer where D2 is acting as the select line. If D2 is 1, D1 is selected. This is the normal behavior of the circuit. If D2 is 1, then whenever clock comes, D1 will go in. Exactly that thing happens. If D2 is 1, if clock comes, D1 will go in. But if D2 is 0, here the clock was not coming at all, but here you cannot stop the clock from coming, clock is directly connected. So, here what you have done, that the output whatever is there, that same value will come. So, the value of the flip flop output will not change, the same value will again be stored once more if D2 is 0. So, by making a small change, we have eliminated the design rule violation, and this is also not an asynchronous feedback, because feedback is taken from the output of a flip flop. Okay. So, this is perfectly allowed. Well, and the second thing I mentioned, that in scan design all the flip flops must be converted into scan flip flops. Okay. So, let us see how this scan flip flop looks like. So, a scan flip flop looks like this. You can forget this portion for the time being. The rest is a conventional master slave latch. The master stage, the slave stage, and the clock is coming. The master is clocked by the clock high, and after inverter, slave is latched. But in the scan flip flop, actually what we are doing is that you have the flip flop. This was the flip flop, clock was there, clock is still coming, but the data input which was there, you are connecting a multiplexer out here. There are two inputs to the multiplexer, one is the normal data input, one is the scan data, SD is the scan data, and the test control input is controlling the multiplexer. This is actually functionally what is happening. So, the test control is deciding whether the normal data input will go in or the scan data input will go in. Okay. Now, let us see that how this kind of a structure can be configured, so that in the test mode the flip flops behave as a shift register. Okay. Let us see. So, the modification is done like this. Normally, we had a combination logic, some flip flops with feedback. Now, these flip flops had been converted into scan flip flops. Now, scan flip flops, in this diagram there are 3 inputs. The inputs are in this order. The top input is the normal data input D. The second input is the test control, and the third input is the scan data. Okay. Now, you look at the scan data pins. I have shown it by dotted. I am highlighting this path. Suppose test control is high. So, instead of D going in, now scan data will go in. You just look at the previous diagram. If TC is high, SD will go in. Okay. So, this is SD input, this will go into the output, get latched, and the output of this is feeding the SD of the next flip flop. Output of this is feeding the next SD, and in this way. So, you see that through this SD, these flip flops are changed into a shift register. So, whenever this TC sets the circuit to the test mode, the flip flops are all in the form of shift register. There is a scan in, there is a scan out. Through this you can feed data and you can observe. Now, scan in and scan out can be some of the primary input and primary output pins also. If you have extra available pins, you can use them as a dedicated way, but TC must be a separate pin. Okay. So, and if TC is 0, which means the circuit is operating in the normal mode, then the D input whichever was there, the normal input, this will be going out, this will be going out, this will be going out, and the same value will be fed back. This is the normal mode of operation. Okay. So, in this circuit you try to observe that for applying each test pattern, what we have to do. For applying each test pattern, I will have to first shift in the data bits into the shift register. Say in this example there are 3 state variables, the 3 flip flops. So, I need 3 clock pulses for doing that. After that, I will be applying the primary input and apply another clock, set the circuit to the normal mode and apply a clock pulse. So, after applying the clock pulse, I can see the primary output, and these outputs will get latched into the flip flop. Then again I set the circuit to the test mode and I again apply 3 clock pulses, so that the next state which is coming out will be observed on the primary output. So, in this way I can control and observe. Okay. Diagrammatically, this diagram shows in the axis of time what happens. This is the combination logic, these are the primary inputs you are applying, these are the primary outputs which are going, this I1, I2, O1, O2 are in sequence, and this present state S1, S2 and the next state N1, N2, these are shifted in and shifted out. So, you need additional clock pulses for feeding the present state and observing the next state. Okay. So, scan in and test control are the control inputs. So, now let us try to estimate that how many clock pulses we would need for doing this whole testing. Okay. Well, now I told you earlier that before we actually start testing the circuit with the combinational test patterns, you will have to test the shift register. Okay. So, first let us see that how we can test the shift register, because shift register testing is very important, because unless you are sure that the shift register is working correctly, you cannot really start testing the combination logic. So, there are standard ways of testing a shift register. What people normally do is that if you have, let us take an example. Suppose you have a shift register with 6 stages, a 6-stage shift register. You want to test it. Now, you apply a continuous shift sequence of 0011 0011 to it. You apply 0011 0011 and all the bits you apply, they will have to come out of this. Now, how many bits you will be applying? If there are n SFF number of flip flops, here 6, it will be this plus 4. See, the idea behind applying this particular pattern is that if you look at this pattern, then each flip flop in terms of the clock cycles will be assuming value 0, then 0, then 1, then 1, then again 0. So, if you look at the present value and the next value, they are undergoing all possible transitions 0 to 0, 0 to 1, 1 to 1 and 1 to 0. So, actually I am testing all possible transitions in each individual flip flop, and also whatever I am feeding is coming out at the other side, means without any change, without any modification. Then only I can say with some confidence that the flip flop is working correctly. Now, if we have 6 flip flops, you will need NSFF number of clock cycles to feed the data into this and 4 more clock cycles to bring them out. So, you need so many clock cycles to actually test the flip flop. Well, here I am assuming TC equal to 0 is the test mode. Okay. So, test control 0 means the test mode, there you need NSFF plus 4 so many clock cycles. Now, regarding testing, okay. Now, you try to recall what I had said earlier. You have the combination logic, you have the scan flip flops. So, you have a structure like this. Now, for applying each test pattern, what you do? You apply NSFF clock pulses to feed these registers. Okay. So, you need NSFF clock pulses to load this register, so that these inputs are now applied. Then at the same time you can apply the primary input, and then you will have to apply one more clock pulse, this one, so that the output value, new value gets latched into these flip flops. So, if n comb denote the number of combinational test patterns, then NSFF plus 1 into n comb, this is the total number of clock pulses you need to apply the test patterns. And as you are feeding the data into the SFF, at the same time you can go on observing the data for the previous cycle. So, when you are feeding data for the present test vector, you can also observe the response that was generated from the previous test vector altogether. Okay. So, this is the number of clock pulses we will be requiring total, and this NSFF extra term is coming due to that additional feeding and coming out, because for the last pattern, for the last test pattern there is no next. So, for that you will have to explicitly ship them out. So, you will be needing an extra NSFF for the last one. So, this is the total number of clock cycle you need to test the combination logic, and this I have mentioned for the shift register. So, if you simplify this, it comes to an expression like this. So, just as an example, if we have 2000 such flip flops and 500 combinational vectors, then the total scan test length becomes of the order of 10 to the power 6 clocks. Now, in order to reduce the test time, instead of chaining all the flip flops into a single shift register, you can chain them into multiple shift registers, so that you can feed data and observe response onto the multiple shift registers parallelly. So, your total testing time will drastically go down. Okay. So, if you want to have a multiple scan register kind of a scheme, you can do something like this. Well, of course, here I have shown for only one scan, one register, but you can extend it to more. See, the first thing is that these are the scan flip flops, this is the test control feeding, and instead of having a separate scan in line, you have one of the primary input lines acting as the scan in. So, this line will straight away come to here, and similarly the output of this shift register, instead of having a separate scan out line, you can have a multiplexer controlled by this TC, where the output will be sometimes be one of the primary outputs, sometimes this shift register output. So, this is one way you can have scan in and scan out without any additional input or output pins. For the input you do not need any hardware, but for the output you need one multiplexer. Now, if you have several primary inputs and primary output pins at your disposal, you can have several such shift registers in parallel. You can have 10 such, then you will be utilizing 10 primary inputs and 10 primary outputs. Of course, you will be needing in that case so many number of multiplexers, 10 number of multiplexers, one per scan chain. Okay. But even if you use multiple scan register, the point to note is that only one test control is sufficient, and if you are unable to split the shift registers exactly equally, then the test sequence length will be determined by the longest scan shift register, because you will have to scan all of them, only then you can apply the next primary input. Okay. So, the longest scan chain will determine the total time finally. Okay. Now, this scan path is a very good method in the sense that you can have complete you can say controllability and observability of the memory elements, and you can have a combinational testing scheme for testing a sequential circuit. It is very good, but as I had mentioned earlier, nothing comes free. You have to invest in extra hardware in order to achieve this. Now, let us try to see what kind of extra hardware we need in this case. This is a so called scan overhead. Now, scan overhead says that one extra IO pin is necessary. This is the test control pin. In terms of area overhead, well, you observe that you have in SFF so many number of flip flops, and you have converted all of these flip flops into scan flip flops in order to implement scan path. Now, when you are converting a flip flop into scanned flip flop, if you recall, you are adding a multiplexer in the input stage, which means 4 additional gates. So, if you just look at that diagram once more, I have that diagram. Yes. So, here the original flip flop circuit without this required 10 gates. Okay. To make it a scan flip flop, you need 4 additional gates. Okay, this is something to remember. So, with this input, you can calculate the gate overhead like this, where Ng is the number of gates in the combination logic. So, earlier without scan, the number of gates was Ng plus 10 into number of flip flops, because each flip flop had 10 gates. But now after converting into scan flip flop, you need 4 into NSFF this many additional gates. Each flip flop requires 4 gates. So, taken as a percentage, this can be defined as the gate overhead. Just an example, if you have 100k gates in the combination logic and 2k flip flops, then the overhead comes to around 6.7%. But actually this is a rough estimate, you have to make other estimates as well, like I have ignored those multiplexers in the outputs. If you are using the primary outputs to observe the scan outs, you need to consider those multiplexers. And also there are a lot of additional wires you have to lay out now. In order to configure them as shift registers, you need so many additional wires. So, your total routing area will also increase, the total chip area will also increase. That we have not taken into account here. Okay. This is of course the area overhead, but you also incur some kind of performance overhead here. Here the multiplexer delay will be added in the combinational path, approximately 2 gate delays. Flip flop output loading, because the fan out of the flip flop is also now increasing. So, earlier the flip flop was straight away going out, now the flip flop output is now feeding the input of the next flip flop. So, when you increase the fan out of a gate in MOS technology, the capacitive load of the output increases. So, instead of 1, you are now driving 2 gates. So, the capacitive load becomes double. So, the charging discharging time of the output node becomes approximately double and the gate becomes slower. So, in that sense the speed of the circuit drops down. Now, in addition, at the input of these scan flip flops you have a multiplexer, so some additional logic delay. At the primary output you are having a multiplexer, some additional logic delay. Now, if some of these lie in the critical path of the circuit, this will mean that the total speed of the circuit will go down. Of course, the clock frequency has to be dropped down slightly, because the flip flops are now working slightly slower because of the additional multiplexing logic at the input. Okay. So, it has been found that the performance overhead is again to the tune of 5 to 6%. So, you are getting a number of advantages, fine, but you are also paying some price. You are paying for more area, you are paying for a slower clock. So, if you are trying to build a very high performance circuit, then you will have to think about something else also. Just a pure scan path approach may not be very desirable in that case, because you are making your circuit slower. Okay. So, the way this scan path is actually implemented in CAD tools is that you can do it hierarchically. Like well, instead of considering the whole circuit as a whole and totality, and we incorporate scan and do it, you can do it in a hierarchical fashion. Like suppose in this block you have a hierarchical netlist, like during your say the circuit partitioning or placement you had 4 different blocks. So, I am not showing the different blocks, I am only showing the flip flops. Say there are different blocks in your circuit where there are flip flops. So, without loss of generality I am showing only one flip flop in one region, but it can be more. Say this is one region, this is one region, this is one region and this is one region, and this is how they can be connected. Now, if you had a flat layout, then all these flip flops would be connected in a single scan chain like this, okay, like this. They will be connected in a long scan chain, but here what I am saying is that, well, here also the same thing is true, but instead of considering the whole circuit as a whole, you do it hierarchically. When you are developing this small module, what I am saying is that when you are developing a small module, you develop this module with scan chain. This is the scan chain, say I am showing it like this. You develop another module, this also will have a scan chain. This another module, this would also have, say, a smaller scan chain. Now, these modules you are developing hierarchically. Now, when you put all of them together on the surface of the silicon and try to interconnect them, you can also integrate the scan paths. So, now this will be your scan in and this will be your scan out. So, instead of considering the whole circuit together and doing it, you can do it individually. This helps you in saving time in testing, in the sense that, see, the test generation and fault simulation algorithms, they are pretty complex. They take time which is more than of the order of n square, where n is the number of gates. So, if you can break the whole circuit into a number of smaller circuit and apply these to the smaller sub circuits, then the total time that you require will be much less in general. Okay. So, that is why this kind of a divide and conquer approach helps in reducing the total time that you need for testing. Okay. So, just to summarize this scan path approach, scan is the most popular design for test unit technique which people use nowadays. It is a rule based design. There are a set of well defined rules. Now, since the rules are so simple and systematic, they are easily integratable, they can be easily integrated into the commercial CAD tools. Most of the commercial CAD tools have an option to insert scan path automatically. Okay, you can do this. And if you do this, if you have a full scan, which means all the flip flops are in the scan path, you can use combinational automated test pattern generator for generating the test patterns. So, the advantages are obvious. You can have better design automation, you can have high fault coverage because the combinational ATPG works much better as compared to sequential. You can have hierarchical approach if you want, moderate area and speed overhead, which can be tolerated in most cases, other than extremely high performance design where you want to increase the speed by all means. Other than those applications, for most other applications this overhead can be acceptable. Okay. There are disadvantages also, as we had seen. We need additional pins, we need additional test hardware which can slow down the clock, large test data volume, because for applying each individual test we have to apply so many clocks and so many shifts. So, the total testing time is increased, and this is a slow speed or DC test. See, this is called slow speed test to distinguish this from another kind of a testing which is called at speed testing. Now, at speed test is a mechanism where you are testing the circuit at the clock frequency at which it is intended to work. But here, since for each application of the pattern we need to shift the data in the shift register, we are not making the circuit work at full speed. Okay. So, if we could apply the input patterns one by one, apply clock at the maximum speed, that would be the at speed testing, but here we are applying the test patterns at a much slower clock rate as compared to the intended speed of operation, because the controllability and observability is making the process much slower. Okay. So, I am just showing you overall picture. See, you have the gate level netlist here. So, what we normally do in a typical VLSI design flow, we have a gate list, we have a gate netlist here which we have obtained through synthesis. So, using some tool from the gate level netlist, you can carry out scan hardware insertion. So, some of the flip flops will be made scan flip flops and the scan paths will be made. So, after this insertion, you can go to the chip layout, you can optimize the scan chains, and you can also see that whether the timing requirements are satisfied. Okay. Now, in order to do the scan chain optimization, a process called scan chain ordering is done. We are not going into the details of this. So, some sort of an ordering of scan chain may be required. So, depending on the scan chain order, you now generate something called scan sequence and test program generator. These are the actual patterns which will be told to the automatic test equipment. So, the AT will blindly apply these test patterns to the circuit. Okay. This, in order to do this, you also need the combinational test pattern generator which have been generated by a combination ATPG. So, this total pattern which you find out from here, this is applied to the actual chips which you fabricate, and this will be your test program. So, these are the roughly the, you can say, entire flow, and in the gate level netlist, if you see that if there are any scan design violations, you can go back and make some changes and again come back. Okay. So, this is the whole picture. Now, I told you that it is not mandatory to have all the flip flops in a circuit present in the scan chain. You can have something called partial scan also. Now, let us see why this is required, what is the motivation behind having partial scan. Well, obviously, partial scan means a subset of the flip flops are scanned, and some of the objectives which are listed here are also obvious, it follows from this. Since we are not converting all of the flip flops into scan flip flops, so area overhead is reduced and scan sequence length is also reduced. Some of the selected flip flops are excluded from scan. There are ways to do this, we will talk about this. This can improve performance as compared to full scan design, and you can have faster sequential ATPG. See, I will just come to this point in the next slide. Shorter scan sequence I have already mentioned. So, the partial scan architecture will look like this. We have a combinational logic, there are the flip flops. Some of the flip flops you convert into scan, some you do not. So, for these two flip flops, this and this, you can treat that these are part of the primary inputs. Similarly, these two outputs. But for the other two, they still remain a conventional sequential circuit. So, if you have partial scan like this, one thing is true, that by chaining them into a shift register, you are unable to have complete controllability and observability of all the flip flops. This means that you cannot use a pure combinational circuit test generator to generate the patterns. You need a sequential test pattern generator to generate the test patterns. but one thing I told you that a sequential test pattern generator is more complex, it takes much more time to generate test patterns as compared to combinational. But from experience we know that what are the kind of scenarios which can make the sequential test pattern generator more difficult. So, here our idea is that we try to identify or classify the flip flops as which of those are more difficult with respect to sequential ATPG, which of those are not so difficult. So, the difficult ones we convert into scan, the not so difficult ones we leave as it is. So, our idea is we have a sequential circuit with flip flops all right, but with respect to sequential ATPG that will be not much of a problem, because the problem cases we have eliminated. Okay. So, there are a number of different techniques which have been proposed for selecting these scan flip flops. The first approach is based on some testability measures. Well, there are several standard techniques. One popular method is co-op. Here you can statically analyze the circuit and try to find out the controllability and observability metric of each individual line. So, you can find out which of the flip flops are more difficult to control and observe. So, you can select those as scan flip flops. You can have some structure based approach, like you convert the circuit into a graph structure where the nodes will be the flip flops and edges will be paths from the flip flop output to the input. You try to break the cycles there. If there are 3 flip flops which you see they are lying in a cycle, you make one of them a scan flip flop. So, this flip flop is no longer there in the conventional sense. So, you have broken the cycle. So, if you break the cycle, then cycles in the flip flops are not there, which are more difficult for sequential ATPG. Secondly, you try to have some kind of balance structure, that means the number of flip flops that can lie in cascade, you limit that to the same value in all cases. So, these all help in sequential ATPG. So, combinational sequential test generation you can do. So, to summarize, partial scan is a technique which is more practical, you can say, because if your circuit has 10,000 flip flops, there is no point in converting all 10,000 of them into scan flip flops. Moreover, you just try to think in a design you can have many registers. Say I have a 32-bit register, I can have 20 such registers. So, 20 into 32 straight away I have about 600 flip flops. Shall I chain them into flip flops? Well, the registers need not be put as part of scan chains. So, this is the flexibility which the partial scan method works, but you can select which are the flip flops you need to be included as part of the scan chain. So, depending on the circuit, the number of flip flops you need to scan can vary from none up to all. And elimination of long cycles in the flip flop paths, I told you, this improves the testability via sequential ATPG. You eliminate all cycles, eliminate all self loops. If you do this, then you can allow combination ATPG also. You need not convert all flip flop into scan path, but you eliminate cycles in the flip flop paths. There are ways in which if you can break the cycles and self loops, you can use combination ATPG for testing. And obviously, partial scan has much lower overhead and less number of test patterns that need to be applied for testing. So, today we talked about some of the design for testability techniques which people use normally. In our next class, we will be talking about another technique which is also used pretty widely, that is called built-in self-test, which means given a chip, we introduce some additional circuit inside the chip itself, so that the chip can be tested on its own. It is a self-test kind of a thing. Okay? So, this we will be discussing in our next class. Thank you.